So in the last class we were discussing the bond model. So in the bond model you understand that whenever a silicon atom get enough energy from the vibration or like photons, muons, electrons and holes, right? Energy it receives from photons, right? Or phonons. Guys, what is phonon? Please let me tell me quickly what is phonon. Last class I explained you. Yes. What is a phonon? So phonon is nothing but elastic wave, right? That is nothing but whenever an atom vibrates, right? It generates some elastic wave. Clear?
Okay, sir.
Yeah. So guys, means did not you understood or you did not answer? Okay. So
Understood, sir.
yeah. So at t greater than 0, whenever a silicon atom is vibrate, right? It get energies from photons. Photons are nothing but whenever atom vibrates, right? It is like oscillating dipole. So whenever a dipole oscillates, it get photon, right? So whenever also a bond broke, right? Whenever a bond broke, we know electron will emitted, right? Leaving behind a hole. So always electron and hole generate in pair, right? So at equilibrium, at t greater than 0, always electron and hole generate in pair. Is it clear? So thing is, and we know we want to estimate the concentration in a qualitative way. Okay, so you know a bond to break a bond, right? Hello?
Yes, sir.
Yeah. So what I'm telling, to break a bond, you know, okay, but how much amount of energy we need? We need is 1.1
1.1
electron
electron volt.
volt, right?
Yeah.
So whenever we want to break a bond, emit one electron and one hole, we need 1.1 electron volt. Is it clear?
Yeah, yes, sir.
Yes, sir.
Yeah. So bond energy is 1.1 electron volt. Okay. And whenever a atom collide, maybe a proton or a phonon or electron or a hole. Okay. Anything collide, right? We get after one collision, averagely we receive 0.026 electron volt. So this is the average energy of a collision, right? So and this is the energy we need for breaking a bond. Okay. So thing is number of particles need to collide or number of particles need to converge at a bond to the break the bond is 1.1 electron volt is the bond energy and 0.026 is the energy of breaking a bond, right? Sorry, 1.1 to 1 electron volt is the energy of a bond. Okay, 0.026 is the energy of collision, right? So approximately 42 number of particles or 42 number of any of them, okay, have to collide at a bond to break the bond and to emit one electron and one hole, right? At t is equal to 300 Kelvin. Clear? Yes. Is this clear?
Yes, sir.
Okay.
Clear.
So
Clear.
yeah. So I need 42 number of particles. Okay. 42 number of particles have to collide. Okay. So then let
I
P is
didn't
the
understand the above point, sir.
oh
That zero
very
point.
yeah, very good, very good. I will explain you. Don't worry. Okay. See this point you want to understand this point right?
Yes. Yes, sir.
Okay. See what I'm telling. A bond, any bond, right? Any silicon bond need 1.1 electron volt energy to break it. Clear?
Okay, sir.
And whenever it get collision of one particle, okay, one particle may be photon or electron or hole, any of them. So averagely, whenever a one particle collide, right, it receives 0.026 eV of energy. Okay.
Okay, sir.
So what I'm telling, if I want to break the bond, 42 particles have to collide at this point, or 42 particles have to converge at this bond, or 42 particle togetherly have to give the energy to the bond, then only the bond will break. Clear?
Yeah, okay, sir.
Yeah, okay, very good. So, guys, you just stay attentive. Okay, so then P is the probability that a bond is met by a particle. Okay, bond is met by a particle means any of them, phonon or electron or hole. Okay, then probability of breaking a bond is how much? P to the power 42. Right? P is the probability of a particle collision. Clear? So what is the probability of a 42 particle? It should be p to power of 42. Clear, guys? Taking that all are independent event. So probability of breaking a bond means p to power 42. Clear or not, guys?
Yes, sir.
Clear. So let P the probability that a particle collide a bond. Then if all events are independent, then p to power of 42 is the probability that a bond will break at t is equal to 300 K. Right? So if there are n atom, right? If there are n atom in the silicon, n atom. Okay. So what is the concentration of electron and hole? So if one bond broke, right? This is the one bond broke. Okay. Okay. So in silicon atom, suppose there are n atoms. Okay. If there are n atoms, okay. What is the total concentration of electron and hole at T equal to 300 K? N atom into, and what is the probability that each atom hit by a 42 number particle? That means nothing but P to the power of 42. Right? So this will be the total concentration of electron or total concentration of hole. Is it clear? This statement is clear to all of you?
Yes, sir.
Yeah. See, P to the power of 42 is nothing but probability that a bond will break. So there are 42 atoms. So there are suppose n atoms. So n atom into each atom hitting by 42 particle probability. This is nothing but total concentration of electron or hole. Okay. So if I want to write mathematically, how it will be? So Ni is equal to, N is the number of atom for same Q. Okay. This is what? Probability of bond energy by Kt is nothing but energy of one collision. Right? Yes.
Sir, actually, how is that p raised to 42? Is exactly how it come like that?
Okay. No. So okay.
Yeah, KT value is 26 milli electron volt now, sir. And EG means 1.1. The same thing, whatever the 42 you have written in EG by KT, correct? No? Yeah, okay, sir.
Yeah.
Ni means intrinsic. Yeah, intrinsic. Okay, sir.
No. Actually, see, let me complete. If you have any doubt, then you will. I think you have some doubt. Okay. So let me complete. Then you will come back to me. Okay. So let me complete this slide. Okay. So what I'm telling, if there are n atoms per centimeter cube. Okay. So always concentration is expressed in terms of per centimeter cube. Clear? Okay. If there are n atom in centimeter cube and each atom hit by particle 42. So here at T equal to 300 K is 42. Okay. If you go to T equal higher, right? So this Kt will be more. So I need less number of particles, right or not? So this is just I given you a mathematics. Okay. So what I'm telling in mathematical, what will happen? So Eg is the bond energy divided by Kt is the average energy of a particle. Then this many number of particles have to collide, right? And so P to the power of Eg by Kt. Is it clear to all of you?
Sir. Yes,
Hello?
sir.
Clear, na?
Yes, sir.
Okay, who could not understand? Who couldn't understand? Guys, if you don't understand, please let me know. I will explain you.
Sir, I got I understood the formula where because due to that division, 42 number of particles need.
No. See. This 42 just I given you a mathematical example. Okay. 42 just you forget it. Okay. So.
I mean, I got the point, but how that p raised to 42 actually came, sir?
Okay.
I mean.
Wait. I will let you know. See. Now see, Eg is my bond strength. Okay. Hello,
sir.
Eg is my bond strength. Okay. Divided by, if I want to break the bond, how much energy you need?
0.026. No, 1.1.
Kt is the average energy of one collision right?
Okay.
E is the bond energy.
Okay.
So if you want to break the bond, how many number of collisions you need? We need Eg divided by
By KT.
Kt. So this is the number of collision at a bond or at a atom we need to break this bond.
That I understood, sir.
So
but
wait.
that
That you understood? This you understood? This is the number of collision at a bond at a atom for breaking the bond. Clear? Is it clear to you or not?
That's clear, sir. That's clear.
Clear. So this is the number, right? This is the number. Eg by Kt is the number of collisions, right? This is the number of collisions. Okay. So if P is the probability of one collision, okay, right? P is the probability of one collision, then what is the probability of this much number of collisions? Will be P power of Eg by Kt, right? So this is the probability of Eg by Kt number of collisions, right?
Sir, actually, probability comes number of possibility by possible number of outcomes by total number of outcomes. No, sir. You are writing in power. He is asking why in power. That's what.
Yeah. What I'm telling. See, P is the probability, right, of one collision. Okay. So if there are two collisions, right? Two collisions are independent. It should be P power 2. Right. So there is an atom. Okay. Atom.
Okay, sir. Now I got it.
Okay.
That
So
independent.
if I want three collisions, so it should be P into P into P. So I need three independent collisions, right? So it should be AND, not OR.
That
So,
makes sense, sir. I understood, sir.
three collisions have to have met, then only back will bond.
Okay.
Example, I have 42. So P into up to 42. So all have to take place. Then only the back bond will break. Clear?
Yeah, sure.
Okay. So I think you understood the point. So this is the number of hello? Tell me.
Yeah, sir. Ni means, sir.
No, I'll go to that later. Wait. So first thing is, you understand that key, if for a atom get break, a atomic bond got broken, either this probability, right or not?
Yes, sir.
So if there are n atoms, right? So what is the probability that means this is the probability that one atom meet one. This is the probability. Okay? This is total probability of one atom get collision. Okay, if there are n atoms, so what is the total number of concentration? It should be n into this, right or not?
Yes, right, sir.
Yes, means n atom into each atom. What is the probability the bond will break? Clear? There are n atoms. So what is the probability that each atom will break? Each atom will collide. Okay.
Yes, sir.
Yeah. So all of you very clear now?
Very clear, sir.
Very clear. Okay. So this is the Ni is the concentration of carrier in the intrinsic semiconductor. Somebody asking me. So Ni is concentration for CMQ. Okay. Of electron or hole. Okay. In intrinsic semiconductor. Guys, clear? Yes.
Clear, sir.
Okay. So let me clear this if you understood.
Sir, can you explain little bit slower, sir?
Fine. I'll explain it slowly. Okay. Not an issue. So till now you understood, no?
Yes, sir.
From now on I will go slow. Okay. From now
Okay,
onward, I will go slow. Even if you need more slow, you let me know. Okay.
Okay, sir.
Okay. Fine. Okay. So guys, all of you understood the formula. N Ni is the concentration of electron is equal to concentration of hole, right? Because at equilibrium, the electron and hole generate in pair, right or not? Hello?
Yes, sir.
So Ni is the concentration of hole or concentration of electron in intrinsic semiconductor at equilibrium. Clear? So it should be equal to, it is the number of atoms per centimeter cube into probability that each atom will collide by to get a bond energy. It is the probability of Eg by kT. Clear, guys?
Sir.
Clear. Okay. So guys, from this expression, can you tell me the intrinsic concentration depend upon what? This is qualitatively. Can you tell me? So from this formula or from this formula you derived here, right? So the intrinsic concentration should be depending on what? Guys, come on, it's very easy question.
The concentration.
See, this Ni, I am telling, depending upon what? You see the formula, right? Hello?
Hello, sir.
Now, why it is taking so much time? Because see, I have written the formula. I'm asking a question. The intrinsic concentration is depending on what?
The total number of charge carrier.
No. You see clearly. Okay. So the intrinsic semiconductor, the intrinsic concentration depending upon temperature and also the energy gap. Clear? For bond energy.
Okay.
Okay. So for different so for different semiconductor, okay, have different energy gap or different bond energy. So there should be different concentration, right or not?
Yes, sir.
Yes. And you were asking me how this 42 number come, right? This 42 number just at 300k, right? So if you go to 500k, right? So this kt will increase to suppose 0.03, suppose. Okay. Then number of particles will be 1.1 divided by 0.03, right? So it will be less, right? It may be 30 or something, right or not?
Right, sir.
Right. So if you go to higher temperature, right, the average collision energy will be increasing, right? And the number of particles needed for the breaking a bond will also decrease. Hello?
Once more, sir.
No. Actually, someone, okay. What I'm telling, if you go to higher temperature, okay, so KT will increase or not?
Yeah, sure.
If I go to higher temperature, KT will increase. KT is nothing but average collision energy.
Yes.
Yes. So when KT will increase, what will happen to Eg by KT?
It will
Is
decrease.
constant, right? Eg is constant, right? For a semiconductor, approximately.
Yes.
The bond energy is constant. The collision energy is decrease. So the number of particle needs to break a bond will decrease or increase if I go to high temperature.
Number of particles will increase.
No.
Decreases.
So, Chaitra, you were telling me to go slow.
No, sir. Is it fine, sir?
Fine,
It is
no?
fine.
Fine. Okay. So see, actually see, guys, you concentrate a little bit more. Okay, then you will get the point. Okay, what I'm telling, if I increase temperature, right, this KT will increase. Hello?
Yes, sir. KT will increase.
KT will increase. Then what will happen to Eg by KT?
Eg by KT will decrease.
So what is Eg by KT? No? Eg by KT will decrease. Then what is Eg by KT? EG by KT
the
is nothing but
number of
number of particles need to collide at an atom to get electron hole pair.
Yes.
So it need less number of particles to get collide.
Yes.
Yes. Then the probability is increased, right? So suppose it is P power 42, it may go to P power of 25, something like that. If you go to high temperature.
Yes.
So thing is, if I go to high temperature, the probability of making a bond will increase or decrease?
Decreases.
What will happen?
Decreases, sir.
No, if I go to
It's
high
less
temperature,
than less than 1, so it will increase, I guess.
Increase, exactly. So I'm telling, if I go to high temperature, the probability of breaking a bond will increase. I don't know.
Yes, sir. Because 1 by infinity will goes to P power 0, 1 and it will go N.
Reading?
Yes, sir.
P is equal to suppose 0.8. Okay, let me tell you. Okay, so 0.8 power of 10 is more, or 0.8 power of 5 is more. Which is more? Which is more?
0.8 power 5 is more.
More. So if you go to high temperature, this is exponentially decreasing or increasing?
It will increase probability.
Why will increase? That means number of concentration will increase or not?
Number of particles will decrease.
Number of particles will decrease. So the electron hole pair will increase or decrease?
It will decrease due to number of particles are less, right?
No. You actually were missing the point. See what I'm telling? If I increase the temperature, right? So Eg by Kt will decrease, right or not?
Eg by Kt will decrease. Okay.
So if Eg by Kt will decrease, Eg by Kt is the number of particles that need to collide. Right?
Need to collide. Yes.
Yeah. So now I need less number of particles to I need less number of particles to collide to break the bond.
Okay.
So it is easy for me or difficult for me to break the bond?
So it's easy for us to break the bond.
Break the bond. So if easy for the break the bond, then the concentration of electron and hole will increase or decrease?
Okay. Surely increase, sir. Surely increase.
Okay. So all of you got the point now? Chetan? Check? Theory?
Yes, sir. Got it.
Got it. Chetra, you also got?
Yes, sir. Got it.
Okay. So I think all of you got it. So let me move forward. Okay. Now, this is a very important question. Okay. It come in the exam. Okay. See, always don't look at the mathematics, right? So I always suggest people, do not look at the mathematics. First to understand intuitively. So if I increase temperature, the atom will vibrate more, they will have more energy, bond will break, the catalyst will generate more. It is very easy. Don't need to see the formula also, right? So you should see qualitatively. If I increase the temperature, the atoms will vibrate more. There is a lot of energy in the crystal. Then it is easy to break the bond, right? So there will be more concentration of electron and hole, right or not?
Right, sir. Right.
Right. So this should be very easy for you, right? You should not take so much time to think this. This is a very easy concept, na? Okay. So now you see. Okay. There is a question. Okay. Question have come in the exam. The bond model gives accurate estimation of concentration of charge carrier, rough estimation of concentration of charge carrier, mobility of charge carrier. What is the right answer? Right? See,
Accurate estimation of.
no, how it got just giving you a qualitative view. You don't know
Yeah,
the probability. See, you don't know the probability, right? You do not know.
Yes, sir.
You know EG, you know KT, you know N. You don't know P. Just giving you qualitatively how the concentration should depend on. It should depend on the energy gap or bond energy. It depends upon the KT. So it's telling that my concentration of electron or concentration of hole in intrinsic semiconductor depends on the bond energy, also depends on the temperature. That's what it's telling. Okay, and he's not telling you ki, suppose I will ask you, tell me the concentration of electron at T is equal to 350 K. Can you tell me exactly how much? Can you tell me? Hello? Hello? Hello, am I audible?
Yeah, yes, sir.
My question is, if I want to tell you, tell me the concentration of electron at temperature T is equal to 350 kilo Kelvin for silicon. Can you tell me from this model?
We need the probability also.
That is not known, that is just a probability, right? So we don't know the exact probability. So this
You get rough estimation, sir.
exactly. So it gives a rough estimation. Like it will tell you to appreciate. Suppose if I increase temperature, the concentration will increase. It will just give you a feel of how the credits are generated. It won't give you exact concentration. So the exact concentration will be given by band model that we will research next. Okay.
Okay.
Okay. So the next chapter is band model. Okay. So okay. So log Ni versus 1 by T gives what? Yes, tell me clearly. So take log Ni in this.
Carrier concentration at equilibrium.
No. You see this. What is the question first to tell me? Question is telling me there is a curve. Okay. Log Ni in x-axis and in y-axis 1 by T.
Temperature increases, log Ni also increases, sir.
No. Actually, it's IFM. So I made this. Tell you. Okay. So this 1 by T gives what? The question. Understand the question? So slope of log Ni versus 1 by T curve gives what? This is the question. Tell me. Now you tell me. So let me tell this. Take this one here. Okay. Let me tell you. So if we take log Ni equal to log N plus log heat power of Eg by Kt. I don't know. Right? Right. So if I take this means log N plus plus
Eg by Kt log P.
yeah. So Eg by Kt log P. I don't know.
Right.
Now log N plus, or I can say, because log P is less than 1, right? So 1 by P should be greater than 1. I don't know. So I can write Eg by Kt log 1 by P. Did 1 by P is a positive number? 1 by P is greater than 1? I don't know.
Right.
Right. So what I can say, this is log Ni. So log Ni versus 1 by T. Okay. So log Ni is equal to log N minus 1 by minus Eg by K into log 1 by P into 1 by T. Okay. So we can see log Ni versus 1 by T, right, can give me the Eg. I don't know, right? So if I plot log Ni versus 1 by T, I will get like this. So the slope
Sir,
will be
it's in the y equal to mx plus c type form, but
exactly right. That's right. So y equal to mx plus c. So this is in x-axis. This is in y-axis. Okay, log Ni 1 by t in x-axis. Okay, if you take a plot, the slope will be this one, minus Eg by k log 1 by p. I don't know.
Right, sir.
Right. So what it will give me? So log Na versus this can give me my energy gap. Clear?
Yes,
Okay,
sir.
okay. Okay, sir.
All of you clear now?
Clear, sir.
Clear. Okay. So the concentration, let me omit it, okay? The concentration in intrinsic semiconductor, right? What is the answer? Independent of temperature, increases exponentially with decreasing in Eg, increase linearly with increased temperature, increase non-linearly with increased temperature. Which one is right? See, this is the question. Okay, you have to answer in less than 30 seconds. Okay, because HIL or whichever exam for engineering service, you have to answer this kind of question 30 seconds, provided you are very clear with the subject. Okay.
It increases with linearly increasing in temperature, sir.
Which one? 1, 2, 3, 4. Which option is right?
Third one.
Third one. So third one. Someone else? Which one?
Fourth one.
Third one only, sir.
Third one only. Okay. See.
Sir, actually, it's a non-linear
Very
relation,
smart
right?
one, right? It's very smart. Okay. Ni is dependent upon exponential to the temperature, right? Exponentially. Okay. Is exponentially is a linear curve?
No, no.
No, sir.
Then how third one should be right? Should be
Yes,
fourth
sir.
one. No?
Yes, sir.
Clear? This is not there. Okay. So only this four options are there. Okay. See, carrier concentration, it is independent of temperature. This is wrong, right? Dependent on temperature. It increases exponentially with the decrease in Eg. No, if increase Eg, it also will increase. It's not like it should be increase in Eg. Clear? So it increases exponentially with increase in Eg. It's not decrease in Eg. Right or not?
Right, sir.
Right. So this is also wrong. And increase linearly with temperature. So if your temperature increases, it increases exponentially. Right? If you see, it will be law Ni versus if you see temperature versus Ni, it would be like exponential. Okay. So it is increasing linearly with temperature. Is this question clear to all of you?
Clear, sir.
Okay. Let me. Hello, everybody understood the question?
Yes, sir.
Okay. See, you guys be very attentive in the exam, also in the class. Okay. Because the thing is, everybody can answer this kind of question, but you should answer in very quick time. That is very important. Okay. Okay. So, guys, this is very important one, band model. Okay. So 90% questions will come from this model. Okay. So EDC means what I can say in EDC, if you understand band model, so you can say 50% of your job is over. Okay.
Okay, sir.
So okay. So let's discuss this band model properly. So let me take just 1 minute break. Okay. Then I will come back. Okay.
Okay, sir.
Yes, I am back. Okay. So thing is, from the bond model, okay, we got a qualitative understanding of what should be the concentration, right? So if someone want the concentration of electron or hole very accurately at any temperature, then how to do, right? This is the aim. Okay. So the main aim of bond model is it gives me very accurate concentration of electron and hole pair. Okay. Clear?
Clear, sir.
Okay. So what is a band model? So a band model is like nothing but we will try to estimate the concentration of electron or hole in a semiconductor on the basis of how much of energy, right, a carrier is having. Okay, like you see, before I go to, so before first let me tell you the model, then I will explain the analogy. Okay, so this band model try to estimate the concentration of electron based on the energies possessed by the electrons or carriers. Is it clear to all of you? Hello? Hello?
Sir, can you tell once again?
So what I'm telling, this model, right, try to estimate the energy, try to estimate the concentration, okay, based on the energies possessed by the carrier. Okay, so first let me tell you what is the model, then you will convince. Okay, so first let me tell you. Okay.
Okay.
So first thing is we want to suppose in a silicon, right? Suppose in a silicon atom. Okay, so let me first go to this. But let me tell you analogy, then I come back to the model. Okay, suppose in a building. Okay. In a building, you want to estimate the number of people presently are there. Okay, guys, this is the problem. Okay, so what I want to find out, how to find out the number of people staying in the building. Okay, suppose this building is having 10th floor. Okay, so 1, 2, up to 10. Okay, this is 10th floor building. So in the building, you want to find out the number of people staying. Okay, so then what you will do, you will go on counting. So in first building, how many people are there? Okay, in second building, how many people are there? In 10th building, how many people are there? Then you have to sum it all of the people, right or not?
Right.
Right. So similarly, in semiconductor, right? Suppose silicon. Okay, so silicon is having 14. The atomic number is 14. Right or not? So one silicon atom is having 14 electron. 14 electron. Clear?
Clear.
Clear. So similarly, out of 14 silicon atom, we know the atomic is like 1s2. So if you go to chemistry, right? So the silicon atom, if you see, right, 1s2, 2s2, 2p6, 3s2, 3p2, right? So 1s2, 2s2, 2p6, 3s2, 3p6, right? So 1s2 means what? There are 2 electrons in the first orbit, so the energy of the first orbit will be low. Then there will be, this is 1s2. Okay. Then there will be 2s2. So energy which there are 2 electrons in the second orbit, 2s2, having energy more than 1s2, right or not? Hello?
Right.
Right. Similarly, I will get 2p6, I will get 3s2, 3p6. Okay, so in a silicon atom, out of 14 electron, there are 2 having energy in 1s2, then 2 are having 2s2, then 6 are having in 2p6. Okay, similarly 3s2, and in 3p6 out of 6 we are having only 2 electrons, right? Only 2 are present. Okay, so what I am telling, out of 14 electron, different electron have different energy, right or not?
Right.
Right, and also you can see the electrons are distributed not uniform energy, right? So let me go to the terrain now. Okay, so bond model try to find out the concentration of electron based on the energy of electrons. Like here, like it will try to find out at this level, okay, how many electrons are there? At this level, how many electrons are there? Okay, so if you can add it, then you can get total electrons, right or not?
Right.
So the model try to find the concentration from the energy that they have, the electrons have. Now, Chitra, understand the point of the model?
Yes, sir.
Okay. So again, see, think this is, then if you go in depth, now you will get the complete point. Okay. Now you have understood ki what this band model is, right?
Right.
Okay. So the band model calculate the concentration from the 3 points. One is allowed energy state, second is distribution of allowed energy state, and third is what percent of energy states are occupied. Okay. So each and every point I will explain you one by one. Okay. So first thing is what is the allowed energy state? Okay. So since we have seen here, out of the electrons are not allowed in any energy, right? There is some fixed energy like 1s2. Okay, then after some time we get to 2s2. So the electrons are not allowed in between, right or not? Similarly, in between this energy, so this is energy E1, this is E2, right? So in between E2 to E1, there is no carrier, right? In this energy, right or not? So there are 2 electrons at E1, there are 2 electrons at E2, but between E1 to E2, is there any electron are there?
No.
Right. So out of 14 electron, there are 2 electrons at energy E1, 2 are at E2. So in between, suppose I want to find out any electron there in between here in this energy, not there, na? No. So what this is telling? The electrons in a crystal are allowed only certain energy levels. Okay, it cannot stay anywhere. Right or not?
Right.
And out of the allowed energy stable, right? So they are allowed only at certain energy state. Out of the allowed energy stable, they always try to occupy the lowest energy available. Clear? Like
Clear.
out of 10th floor, okay, if I tell you, you will try to stay ground or first floor, right? No, you will not try to stay in the 10th floor, right or not?
Right.
Right. This is the thing. Third thing is, no two electrons occupy the same state. Okay. So suppose in one floor, suppose you need only one room. Okay. So in a 2 BHK, you have 2 people. We always try to stay in two separate room or only one room. Hello.
What did you ask, sir?
See, what I'm telling. First thing is, the electrons are allowed only certain energy level. Okay. So after the allowed energy level, they always try to stay in the lowest energy available. Okay, like I'm telling, in a 10th floor building, you will try to stay first floor or ground floor only, right?
Okay.
Okay. And also in first floor also, suppose you have given a 2 BHK. Okay, so there are 2 people. Then always you try to stay 2 people in 2 room, right? Not in 1 room, na?
Okay. Understood, sir.
So this is the thing is, no 2 electrons occupy the same state. Okay, so this is the allowed energy state. Okay, and how it will come, I will explain you. Okay.
Okay.
Then this is called after suppose distribution of allowed state over the energy. Okay, for example, see, suppose this 2 PCC is allowed. Okay, but in this 6 people are allowed. Okay, but here only 2 people are allowed. Okay, so what are you telling? The distribution of energy state over the energy is not uniform, right?
Right.
I can say in first floor only 2 rooms are available. In second floor maybe 5 rooms available, or in third floor maybe 7 rooms available. In 10th floor maybe 2 rooms available. Okay, so the distribution of rooms over the floor is not uniform. Okay,
Right.
guys, all of you clear? Hello? Clear. Okay.
Yes, sir. Clear, sir.
Okay. Very good. So now it comes to the important point. Okay, so we will discuss each of the 3 points one by one. Okay. Also thing is, out of the allowed state, then third point is what fraction of allowed states are occupied. Okay. Suppose in 10th room, 10th floor, 2 rooms are available. Okay, but if you want to find out how many people are staying, so out of 2 rooms, what is the probability that these 2 rooms are occupied? Then only you will get the number of people, right or not? It's not like suppose in 10th floor 2 rooms are available. It will not give you the number of people. Also, you should calculate out of 2 rooms, how many rooms are occupied, right?
Right.
So third point is out of the available energy, what is the probability or what is the fraction of available energy is occupied? That will give you the total concentration of electron. Clear?
Please.
So let me explain you each and every 3 points. Okay, so I will take maybe half an hour or so. Okay, to explain these 3 points. If you understood these 3 points, then you are done and dusted. Okay. So Chitra, am I going fast or my voice is okay to you?
Yes, sir. It is fine for me, sir.
Fine for you. Everybody is fine, na?
Yes, sir.
Okay. So let me go to the first point. Okay. So we call allowed energy state. Okay. So this is the only complicated thing. Okay. If you understood this much, then rest thing is very easy. Okay, guys.
Okay.
Okay. So let me draw. Okay. silicon, okay, having 14 electron, right or not?
Right.
So guys, you listen very carefully. Okay. So out of 14 electron, if you take a silicon atom, okay, so they are occupied, if you say, two P6, PS2, P2. Okay, guys, we know 1 to means there are 2 available states. Okay, 2 to means there are 2 available states. 2P6 means there are 6 available states. Right? 3 means 2 and 3P2 means, but 3P2, but there are in P orbit there are 6 rooms available. Okay, we know this is from chemistry. This is 3P orbital. There are 6 rooms available. Clear? So in first floor, in first floor, out of 2 are occupied. Right? 2 electrons are there. In second 2s2 there are also 2 occupied. In 3P6 all are occupied. In 3s2 2 are occupied. In 3P6 out of 6 orbit only 2 are occupied. Clear? Guys, is it clear?
Yes.
Okay. This is the distribution of 14 electron energy over the energy, right? This is the energy of 14 electron distributed over the states. Clear?
Yes.
Right. Suppose in a silicon there are n atoms, right? N atoms for centimeter cube. Clear?
Yes.
Clear. Suppose you take separate n atom, right? Separate n atom separate. Okay.
Okay.
So then how will have how much electrons we will have here? We will have 2 n electrons in here, right? Here we will have 2 n electrons, right? Because in the if you want to make a crystal, you have to make you have to take n atom per centimeter cube, right or not? See, this is the distribution. This is 14 electrons for 1 atom, right? So in a silicon crystal, we have n atom. Suppose in a crystal you have n atom per centimeter cube, right or not? And suppose you just to take n atom, they are separately, just they are separate. Clear? So if you take n atom like this, okay, any n atom, okay, like I showed the example. You have taken n atom. So in n atom, every atom 1s2 orbital, 1s2, there are 2 electrons. So for n atom, I will have n into 2. I don't know.
Right, sir.
Similarly, for every silicon atom, n2s orbital, I have 2 electrons. So for n atom, it will have 2n. Right?
Right, sir.
Similarly, for every atom, in the 3p orbital, I have 2 electrons. So for n atom, how much will be? 2 into n. Right? Similarly,
Right.
in the 3s orbital of each atom, I have 2 electrons. Suppose I have n atom, then what is the how many electrons per centimeter cube will we have?
2n.
2n. Is it clear to everyone? Hello? Okay. Now see, you have taken separate atom. Okay, you have taken separate atom. Okay. Now what you have to do? You have to do a magic now. You have to plot. Okay. This is the energy. Okay. This is the distance between the atom. Okay. So up to here, they are very separate from each other, right? So this is the distance between the atom. Okay. This is the distance between the atom. This is the energy. Clear? Yes. So
Yes.
you have taken n atom. They are far apart. Okay. So when they are far apart, the distribution is like this. Clear?
Sometimes the voice is not that much clear.
Okay. Okay. Now I'm telling. Now is okay.
It's fine, sir. Now it's fine.
Okay. So what I'm telling, you take n atom, okay, and bring them close to each other, right? So like the distance, right? So what I will try to do, I will bring n atom close to each other to make a crystal, na? Not like an atom will separate, right or not?
Yes, sir. Yes, sir.
Hello?
Yes, sir.
So you bring n atoms close to each other like this. Okay. So you've taken n atom. Okay. So we are reducing the distance between them. Then we are plotting the energy versus how they will distribute. Right. So what will happen? If you bring them right again, if you bring them right like this, what will happen? After some time, when you bring the atoms closer and closer, right? What will happen? Suppose there are here 6 unstate, right? 6 unstate. Here, how many states are there, guys? Here, how many states are there?
2 and 3.
2 states. So if you bring the atom closer, right? Closer, you will decrease the distance like this. What will happen? This atom will try to interact with each other, right? When they are very, very far apart, they are not interacting. That's why every an atom the same energy. Okay, 6 unstate. Okay. Now, if you bring them closer, right? If you decrease the distance, again you bring them closer. What will happen? They will interact. They will interact with each other. Okay, and the energy level will slip.
Hello.
Sir, sir, are you speaking now?
Yeah, I'm speaking. Is it clear?
Your voice is not audible, sir.
Now,
Sir,
okay.
your voice.
Now, okay.
Yeah.
Okay, okay, okay.
So I'm telling, if you bring them closer, right, the atoms will start interacting with each other. What will happen? First, the outer levels, like the outer orbitals, will try to split. The energy will split. Okay.
Okay, okay.
So, like if you see earlier the 6 n orbitals, 6 n states in the same energy. Now there is splitting of energy. 6 n. If you count, there will be 6 n. Okay. So I not. So it's like a continuous 6 n. Like this. Count, it will be total 6 n. Similarly, this also will split. This is split. Clear? Hello.
Okay, sir. Yeah.
Okay.
Your voice is fluctuating, rising, and
Okay.
sometimes
Actually,
leaving up
I
and
have to
down.
I have to means hold the speaker. Okay. Whenever I'm leaving it, it is voice is going. Okay. So now I will try to take care of it. Okay.
Yes,
So
sir.
I'm telling. So if you bring the atom closer, right, the energy 600 is splitting. Even the 200 is also splitting. Clear? Hello.
Yeah. Okay.
Yeah,
Yes,
but
sir.
this 2p6, 2s2, and 1s2, they are inner orbit, right? So they will not interact very quickly. Okay, so you have to go more distance too, so they will not start interacting. So it will be remaining same. Okay, it will remain same because they are inner orbits. Okay, they don't interact so quickly. You have to go very further distance. Okay, then only they will interact. Okay, so initially only these two will interact. Okay, then they will be like a okay. So if you bring this, okay, this is the suppose this is the atomic distance. Okay, this is the atomic distance. What will happen? 6 and state plus 2 and state. Okay, so here we will have how much states, guys? Here how much state we will have total in this? Suppose at this point, okay, at this distance. This is the distance. Suppose this is the distance d, d1. At this point, this is the distance between the atom. Okay, if you bring closer, then at this point all the states are merged. Okay, what is the total number of states it will be at this distance? Total 6n plus 2n, right? This will be total 8n, right?
Okay, okay, okay.
Guys, hello?
Yes, sir,
Hello?
yes, sir.
Yes, let me explain in this. Okay, you see. So these atoms, this is in this you see, when you bring them closer, right closer, the energy will split like this. Okay, so at this distance, I was at this distance, right? I was at this distance. So here I will have total how many states? Number of states here? Total
6 plus
6n plus
2n.
1 is equal to 8n. Okay, so all are overlapping each other. Okay, so you, the metal, right? Metal, it crystallizes at this distance.
Sorry, sir. What was the last sentence?
What I'm telling. So metals, right? The metals, the atomic distance is like this. Suppose this is x. Okay. So if you bring the metal is formed, if you bring the atoms up to this distance, x distance, then what will happen?
Okay.
In this, the total friction states are overlapping. Okay, so out of what is left in this you see.
Not audible, sir. Hello.
Hello, am I
Your
audible?
voice is downfall and it is right fall.
Now
It is
audible?
falling and rising, sir. Yeah, you are audible, but it is falling and rising.
Okay, okay. Actually, next class I will change my earphone. Okay, so now I have to hold my earphone in my hand. Okay, so that is the issue. So next time I will change the earphone. Okay, now it's okay, na?
Okay,
It's
sir.
okay, sir.
Okay. So you see here, here, how many states are there? 8 10, right? Out of 8 10,
Yes, yes.
how many electrons we have? We have 2 electrons in the p orbital and 2 in the
Four.
state. So 4n, right? So this 4n will be occupied. Because I told you the first point is electron will try to occupy the lowest energy available, right?
Okay.
Yeah, yes, sir.
Okay. So in this distance, right? Then for this, this is the point. This is the point where metals will crystallize. Okay, metals. Okay. So at this point, metals are formed when atoms are bringing up to this distance. Clear?
Clear.
Clear. So for the atom, what happens? For metal, what happens? This lower 4n will be occupied. This above 4n will be unoccupied.
Okay. Okay.
Okay. So at t is equal to 0, okay, the occupied and unoccupied are merged. Okay, so they don't need much energy to move from occupied to unoccupied. Occupied means the bond is bonded. Okay, what is the meaning of a bond model? In bond model, occupied means the bond is bonded. Electron is not free. But for metal, if you see, na, the crystalline in this distance, okay, and the crystals are available just above them. So they don't need much energy to move. They don't need any energy to move the free state. So in metal, I don't need any energy to free electron. They are already free because the states are merged here. Clear, guys? Metal.
Clear. Clear. Clear.
Yes. And you might have read somewhere कि in metal both valence band and conduction bands are merged. Okay, that is the meaning of this merged. Okay.
Okay. Okay. Okay, sir.
Okay. So metal crystallizes in this distance. So and this both all the bands are merged. So the electron don't need any energy to move from free the bond. Okay. So that's why metal is electrically conductive at all temperatures. Clear?
Clear. Clear.
And if you go little, if you decrease the distance, so here is metal, right? Here is metal. If you decrease again distance more, okay. So at this distance, here is the distance, okay. So let me to decrease the distance, then they will happen again. They will split like this. This is a quantum mechanical phenomena. No need to whether how it split. So if you decrease them, what will happen? Again the 6n states, so the 8n state again they will split. Okay. So here the whole 8n is merged. Right? If you decrease the distance, what will happen? The 8n will again split. Okay. What will happen? Above will be 4n, and below will be 4n. Clear?
Okay. Okay, sir.
Okay. So if you decrease the atomic distance, then when they merged here, again they will split. They will split into two bands. So the above band is having exactly 4n states. The below band is having 4n states. Right?
Okay. Okay, sir.
Okay. So let me. What happened? This is nothing but my semiconductor. Semiconductor crystallizes at this distance. Okay. That's why what happened? We will have the lower 4n energy, 4n completely occupied. Okay. And this above 4n energy is completely unoccupied. Completely not occupied.
Okay. Okay.
Right? This is 4n state. Okay. 4n state. Here this 4n state is occupied. Clear, guys? So
Clear.
for semiconductor, I get two bands. One is called valence band. Okay. Which is completely filled because out of if you see we have together total 2 plus 2 4n electrons. Okay, so this 4n electrons will be there in the valence band completely at t is equal to 0. Okay, so and in bond model t is equal to 0, all bonds are bonded, meaning is like all the electrons are in the valence band, in this band. Okay, and is occupied, not free. Clear? And all these bonds are empty. So there is no free electron at T equal to 0 for semiconductor. Okay.
Okay. Okay.
Guys, anybody who could not understand? Please let me know. I will explain. Please let me know. And you see this inner orbital, right?
Sir, how conduction band and valence band created, sir?
I will tell you just a minute. See how it is created, na? Somebody is waiting. See how it is waiting, brother. You see. Let me erase, guys. To explain. Let me erase. See, brother. See, if you bring the atom closure, right, like this closure, okay, then this all the 8 state merged here. Clear? Then if you bring even more closure, right? So this 8 state will split into two states, two bands. So first is this much is having 4n state, and this much is having 4n state. So the above states are called conduction band. The below states are called valence band. Is it clear to you?
Yeah, I got it, sir.
Good, na? So it is like at this distance, if the atoms are bringing to this distance, like semiconductor crystallizes at this distance, is the atomic distance. Okay, you may know this is called atomic separation. The distance between two atoms in a semiconductor. Okay.
Energy band gap increases.
No. Band gap is I'm not coming to band gap. What all I'm telling, in semiconductor, the atoms are spaced at this atomic distance. The distance between two atoms in semiconductor is this A. At this point, what will happen? Out of my 8n states, the 4n states are called valence band, which is completely occupied by 4n electron. Okay, and these 4n states are completely unoccupied, completely empty. Okay, because in the valence orbit, I have two electron in the p orbit, 2 electron in the s orbit. Total 4 electron. Total how many states? 6 plus 2, 8 states. Okay, so I have in these 8 states 4 electrons, right? So 8 states and 4 electrons. See, this is third orbital, right? 3p2, 3s2, 3p2, only 4 electrons, but there are only 8 states, right? So for n atom, I have 8n states, and how many electrons are available? 4n electrons are available. Clear? Clear. And at this distance, what happens? 4n electron will occupy the lower energy, nothing but valence band energy, 4n state. Since I already told you, always the electron try to occupy the lowest energy available. So for semiconductor, if you try to bring this here, okay, if you try to bring this here, see, for semiconductor, I have only this much energy available and this much energy available. Okay, in between they cannot stay.
One
Okay.
doubt, sir.
Tell me.
You said 8 electrons are split into 4 and 4, no, sir? 4 in conduction band, 4 in valency band.
Right.
All 8 can sit in valency band, no, sir? Because 8 should be go in lowest energy band.
I'm telling no. There are only 4n electron. 8n states are there. Electrons are only 4n, na?
How we know that 4n it is, sir? In middle it is 4n.
You see, earlier there are 6 states. Okay?
Yeah.
And 2 states in the S2. This is states only have splitted. So 6 state of n electron is 6n state, and 2 states of n atom is 2n state. So I have total 8n states only available. So the 8n states is splitted.
Yeah, that is okay, sir. That thing I got. But why it is only equally splitting 4 and 2? It can split like 6 and 2, like 2 and 6.
Yeah, absolutely fantastic. This can happen, but this is a quantum mechanical phenomena. So what happened, right? If you want to need this to, right? So this needs some 4-5 pages of quantum mechanical derivation. Okay, so for this time you just take it granted. This is like this.
Okay, sir.
Okay, so if you are interested, I will send you some lectures on this, how they got split. It's a very deep, very in-depth quantum mechanical analysis. Okay.
Okay, sir.
Okay, but you take it granted, they split like this. 4 and 4.
Okay, sir.
Okay. So now understand, out of 8n state, 4n here, and 4n is completely occupied, 4n is completely unoccupied. Okay, so this is how we got valence band and conduction band. So generally you might have seen also, you see this 56 2s2 and 1s2. Okay, they are bonded here. You see there is no splitting. Okay, so they will split if you even come closer. That we are not going at all. Okay, so they will split after a very small atomic distance. That we are not going. Okay, so these electrons are not taking part in a conduction at all. They are completely bonded, right? Yes,
Right, sir.
right. So only we have to bother about this much only, right? So you might have seen in book in semiconductor we will have two bands. Okay, this is my energy. Okay, one is called, this is the top of valence band here. That is one ET, EB, and one is called bottom of my conduction band. This point. Okay, and so this valence band is completely occupied and conduction band is completely free. See? At T0 to 0. Now we clear about the band.
Please.
And here, this is not distance. Not distance. Okay. This is just a representation. Right. Just only this point, this part. Okay. I have exaggerated here. Clear?
Please.
Clear. So the semiconductor crystallizes at this atomic distance. Okay. And this point I have taken here, and for your understanding, just to tell you, this is my conduction band, this is my valence band. Okay, so here total we have 4n state, 4n electron. Here we have 4n state, 0 electron at t is equal to 0. Clear, guys?
Please.
Yes, sir.
Okay, very good. Okay, so we have understood the first point. Okay, so meaning is the allowed energy is this only. So the electrons are allowed only in the valence band or conduction band, not in between. This is in between is called energy gap. No states is available. Okay, so electrons are not allowed to stay in between the energy. Okay, meaning is like that ki in this semiconductor, no electron will have energy in between this. If you measure the energy of any carrier, they won't have energy in between. Clear?
At 0 degree temperature, only a valency band is filled. That's all right, sir.
That's all right. That's all right. That's all. That's why valence band being filled, and you don't have any electron to free, electron to move. So electron, there is no free electron.
Valency band is completely filled, and no electron can move even if I apply energy.
No, T equal 0 means there is no energy, na? There is how you are getting energy.
Okay.
Okay. So I will explain you that. That I will explain you. Okay. So let me tell you one more thing. Okay. You might be getting some fun. Okay. So let me tell you. Okay. So let me tell you that it's like okay. Okay. So in bond model, right? A bond model, na guys. So each junction is like a silicon atom. Clear?
Please.
Hello? Clear? So what I was telling, when a bond will break, electron will emit, na? Right?
Yes.
So what will happen here in the band model? So here, this is my valence band, this is my conduction band. It's the same thing, right? One bond is broken and electron is emitted. So what will happen? One electron, okay, will jump from valence band to conduction band. Okay, so I'll get one electron here and one hole here. Okay, so this is the phenomena happening in band model. Okay, so one electron is moved from, become free means it have jumped from valence band to conduction band, and it needs this much of energy is called bond energy is called Eg. Okay, this is my bond energy. Earlier I was telling na, I need Eg of energy to move free the electron. Okay, so whenever a electron from valence band, jump to conduction band, it will become free. And for that I need energy Eg, nothing but bond energy. Clear?
Please.
Clear. So this is the interlink between bond model and band model. This is bond, this is band. Okay, and also you understood what is called conduction band, what is called valence band. Okay, so earlier you might be thinking that okay, there is some bond is coming. Okay, so you should have a picture in your mind. What is this band? How it come about? Okay.
Okay, sir. In the last class, sir, we have talked about the Hall current, where we.
See, what will happen? So in
So
valence
in
band,
this balance band.
valence band you got one hole, right? So what will happen? There are suppose just a minute. Suppose out of 4n electrons, 4n minus 1 electrons are there now. After 1 electron move to conduction band, right?
Exactly.
And we have only 1 electron here. It is moving, freely moving, right? Now what will happen? Out of 4n minus 1 electron, okay, they are bond. So maybe 1 electron from bonded will go to this hole. Again, hole will move here, right? Similarly, same thing. So 1 electron from here will go to this. Then this hole will move here. So this hole will move in the so the bonded electron movement is happening in the valence bond only. Clear?
Clear, sir. Clear.
Okay. So let
Exactly.
me just tell you here. You see, whenever hole, right? Whenever the electron will come here, right? It occupy here and the hole will be created. Okay. So this electron will move from one bond to another bond. Okay.
Yes, sir.
That means it is energy in the valence band only. See. Again I'm repeating. Okay. Earlier electron moved here, right? It have a vacancy hole. Okay. This electron now jump to this, right? And it become a hole here. So the electron come here, become a bond only, na? I don't know.
Right, sir.
So
right.
the energy earlier like a bond only, now also same energy only, right? Of the electron.
Yes.
So thing is, this is nothing but energy only, right? Energy. So whenever a bond electron move from one bond to another bond, the energy of it is remaining in the valence bond only. It's not free. It's not getting so much of energy to move till in the conduction band. Getting? So,
Yes.
so what is the meaning of one electron is here? Meaning is ki it is having this much of energy. So suppose this is 5 eV. This is maybe definitely 8 eV, right? What is the meaning of this electron here? Means the energy of the electron is like this much. Here, so there is electron here in the conduction band. Means the energy of the electron is like this much. This is the energy of electron in the conduction band. The energy of electron in the valence band here. Clear?
Okay.
Getting? So it should be very crystal clear about how it is happening. Okay, because this is the most important thing. Will be carrying forward to every other class. Okay.
Sir, so this valence band current can be controlled by more doping or something?
You don't confuse. Your everything will be clear just subsequently. Now I did not introduce any doping here.
Okay. I understood.
Yeah, the number of bonds will broke. Suppose this will broke. Again, one electron from here will jump to, and I will get another hole. Suppose this one bond will broke. Again, one more electron will go from here to here, and I will get a hole. So the more the temperature, the more the bond will broke, the more the electron in the conduction band, the more the hole in the valence band.
Okay.
Again, I am repeating: the more the temperature, the more easy to break the bond, the more easy to the electron from valence band to jump to the conduction band and generate a hole pair. So the more the temperature, the more number of hole, the more number of electron, and the number of holes is equal to number of electron at any temperature.
Okay.
Guys, clear all of you? Hello?
Yes, sir.
Okay. So we have completed the first point. Second point is distribution of allowed state over the energy. Okay. So what I have told you, This is very easy. Okay, I told you the conduction band is like this, valence band is like this. Okay, so suppose there will be some bottom of the valence band EB, there may be some top of the conduction band ET. Is it clear till now? This is energy E, this is nothing. This is nothing. Okay, this is nothing. This is just a representation. Clear? Hello? Hello?
Yes, sir.
So what I'm telling, so the electrons are allowed in this range and also in this range. Clear? Not in this range, right? Not in this energy gap. Clear? And what is the distribution of allowed state over the energy? So the energy are not so in this range also, right? The energy states are not equally distributed. Okay. Suppose I want to draw this energy, okay, over number of states. Okay. For example, in this question, in this example, what I am telling, suppose I have a 10th floor. Okay, 10th floor, height h1, height 1 meter, 5 meter, 10 meter, 20 meter, 40 meter, or suppose this 60 meter. Okay, so the first building height is between 0 to 60. Okay, so what I'm telling, there are 10 floors. Okay, but in each floor, how many number of rooms are there? So I'm telling 10 number of floors are there, but in each floor, how many numbers of rooms are there? That is important or not? Similarly, here the electrons are allowed in between this energy. Okay, so suppose here in this range, how many number of out? So here we have 4n state, here we have 4n state. I don't know. Yes.
Sir, what is ET and EB? Is a reference or something?
It is the top of the conduction band. So in the crystal, the maximum energy in the conduction band is ET.
Okay.
Similarly, EB is the bottom of my valence band, where minimum energy of the any electron of the crystal is EB.
Okay, thanks.
Okay, and between this EB to EC, how many number of states are there? 4n, na?
Yes.
And between ET to EC, how many number of states are there?
4n.
Hello, guys.
Yes, 4n.
4n. So this 4n are not uniformly distributed, only uniformly distributed of this. Okay, so it is distributed like this, a parabolic function. Okay, like a parabolic function. Okay, it's like, what is the meaning of this? Means suppose in this energy range. Okay, in this energy range. Okay, so in this energy range, more number of n. This is n. Okay, this is n. More number of electrons, more number of states are available in this energy. Okay. If you go here, the number of states is less, right? If you go up, the number of states are more. Getting, guys? Hello?
Not clear, sir. What's
Okay. Okay, let me tell you. Just a minute. Okay. So what is Ne? Yeah. Okay. Ne is number of states, number of states for centimeter cube for EB. Okay. Right. Ne is the number of states per centimeter cube for electron volt. Okay. What is the meaning of this? Suppose this is n. Okay, this is Ne. Okay, this is the number of states per electron volt per energy. For example, like this. Okay, this is a parabolic function. What will happen? Suppose I want to find out how many number of states available out of 4n in this energy D. Okay, so in this energy range, out of 4n state, how many states are available? Is the question clear? Hello? Hello?
Yes, sir.
hello, sir?
Yes, sir.
Yeah, my question is, out of 4n state are not equally distributed. So I'm telling, in this energy range, in this D energy range, out of 4n state, how many states are available? So suppose this is NE. Okay, this is NE. This is the number of states for EV per centimeter cube. Okay, so I want in this range how many available? You will have to do NE
D by D.
into DE. Right. So number of states per electron volt into DE. DE is the electron volt. Okay. So if I want to calculate in this state, okay, how many number of states available? NE into DE I have to do. Clear? It's like getting or not getting?
Yes, sir.
Yes, sir, yes.
Who could not understand? Tell me. See, this is the number of states per electron volt. So if I want to calculate in this energy range, okay, in this energy range, how many number of states available out of 4n? So you have to do what you do? D. So if you approximate this is Ne, okay, like a simple rectangle, should be Ne into D is the number of states per centimeter cube in D energy range. Is it clear to all of you?
Okay. Yes.
Who could not understand? I will tell you in a different way. Please tell me. So, if I want to calculate the total number of states, right? So, what I have to do? Integration of EC to ET NE into D will give me 4n states. Because if I integrate all states together is 4n, but it is distributed like this. So, suppose at this point, the number of states are less. At this point, it is maximum. Right? Here also, number of states are more. Guys, it is clear?
Clear, sir,
Like
clear.
in a 10th floor, in some floor number of rooms are more, in some floor number of rooms are less. Suppose ground floor only parking space is there or security guard will sit, so the number of rooms are very small, right? If you go to a little middle floor means people want to stay in the middle only, so number of spaces are more in this, available rooms are more. Similarly here only, right?
So it became a continuous function, right, sir?
Means for showing you it is continuous. I showed you continuous. Okay, but actually there are 4n states. Out of 4n states, they distributed in this function. Like in this range, the number of states are more. Here, the number of states are less. Actually, there are 4n states. Okay, but so I'm telling in this range there are out of 4n there are many number of states are in this. It's like it looks like continuous, but actually they are discrete. There are very small difference between them. So you can say it is like continuous only.
Okay, so total number of states is 4, and so in between,
but how? So that means what? So about the energy, right? How they are distributed. So
it should be in integral value, right, sir?
yeah, it's integral value. I told you, right? It's to ET, NE into D.
Okay, okay.
So the total area of this will be 4n states. Clear?
Okay, okay, sir. Clear.
So who else in our understand? Please let me know. Please quickly. You have to cover something else and then you have to leave. Chaitra,
Yes, sir.
Chetan,
Sir.
clear. So Sheikh, you also clear, na?
Yes, sir. Clear, sir.
Clear. Very good. I am very satisfied with all of you. Okay. So you understood the total number of states EC to E top should be equal to the number of states per centimeter cube or EV into DE. I have to integrate from EC to ET, will give me 4n states. That's all. Similarly, here also it will be like a parabolic function only. Okay, so it will be integration of EB to EB. Tell me, NE into DE will be giving me 4n state only. Right or not? That's for CMQ. Guys, is it clear? It also. In valence band also, I have a curve like this. Okay, so if I want to know the total number of states, it will be NE into DE over from EC to EV. Clear?
Clear.
Everybody understood, na? So, finally what I'm telling, this is my EC, this is my EV. So, electrons are allowed. So, suppose this is my NE, number of states per electron volt, right? So, if I want to plot, it will be like a parabolic function. Similarly, if I want to plot in the EV, it will be like a parabolic function. This is the energy, E. Okay, so integration of is my suppose EC to E top. Okay, integration of EC to ET, NE into D equal to 4n states. Similarly, okay, getting all of you getting?
Yes.
Okay, and this is expressed in terms of a mathematical expression. So it will be like A1 into root over of E minus EC. Okay, so this is expressed. This is model. This curve is like model like a A1 into E minus EC. Clear?
Yes.
Similarly, this is also model as a A2 into root over of EB minus E. Clear? This is my density of states or distribution of states over energy is this one. In the conduction band, in the valence band. Okay, this is called, okay, distribution of state of allowed state in conduction band is this one. This is the distribution of states in the valence band. Sorry.
Sir, how it became A1 root of E1?
A1 is a constant, simple constant. I'm just telling you, this is a parabolic curve, right?
Okay.
So what it's telling, if you go above energy, that is increasing, right? So E to EC is almost zero, right? If you go above, it is increasing in a parabolic way. So that's what it's telling. This NE I'm just expressing mathematically. Clear? Clear, not clear?
Sir, little bit more clarity on that.
First you understood what is the meaning of NE, na?
Yes, yes.
NE is the distribution of allowed state over energy. Okay, in some energy there are more number of states, in some energy there are less number of states. So this is the curve. Okay, suppose I want to tell you mathematically ki in this range, what is the value of NE? You will just put E is equal to whatever, suppose it is E1. Okay, so let me.
Hello, sir. Voice is not audible, sir.
Yeah. Now okay, na?
Okay, okay.
Okay. Suppose, okay, suppose this is E1, right? This is E1, a value. Okay, so at this
Okay.
energy between D,
Hello.
hello, am I audible?
Yes, sir. Yes.
So I'm telling, this is the energy E1. This point is energy E1. At this point, okay, between this D,
Bit.
okay, now I'm telling, at energy E1, between this D, how many states are available? Okay, question what?
Okay.
So what you have to do should be
N
NE1,
N
N at
E.
E1
Yes.
into D. Clear? So D is the bit of the energy. At what point? At E1 point. At E1, how many states are available? This is NE1 into D. Clear?
Clear, 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 sir.
So it's nothing but a simple rectangular curve. I'm just taking a piecewise linear. I'm making this as a just one value NE, okay, into D, right? NE1 I'm telling. At E1 I have to put NE1. Okay. What is NE1? NE1 is nothing but A1 into root over of E1 minus E1 minus EC. Clear?
Yeah, that A1 root E1 minus EC. That's
A1 into root over E1 minus EC is a value, okay, into D, Either range of energy you want, how many number of states are there? Suppose D is equal to how much? Suppose you take how much? Anything. Okay. So at E1 over a small distance D, how many states are available? At E1 over a small distance D, how many states are available? So at E1, what is the value of NE? NE will be NE1. E1 is I am approximating as this. So at E1 it will be A1 into root over E1 minus EC. It is a value, simple value, right? E1 I know, EC I know, A1 I know, it's a value into D. D will give me the number of states in this D at E1. Clear? See, it's like you have a beaker of water. Okay, I want to find out how many volume of water at this height H1 over this DH is there. So I have to do what? This much water, na? Okay, so okay, suppose this is a glass of water. Okay, so this is water. Okay, completely filled water. Okay, guys. Yes, complete fill of water. I want to find out how much water is present in between this height. I want to know this much water. How much is the volume of this water? Okay, can you understand that the volume of water in this is different from the volume of water in this, na? Right?
Yes.
So the volume of water in this is different from the volume of water in this, right?
Yes.
Suppose this height is dh. dh. This also height also is exactly dh. dh. About the same dh height, okay, the water here is more, the water here is less.
Yes.
And the water here is less is because the NE function here is NE. Okay, this is actually single NE. See here, the curve is less here. The curve is more here. But this height is same, this dh only. I want to find out the amount of water in dh at this height and at this height. So at this height, getting now?
Yes.
So this is H1, this is H2. Okay. So H1 is equal to suppose 1 meter, H2 is equal to 2 meter. Okay. I want in the beaker at height H2 is equal to 1 meter over a range of dh. How many waters are there? How much water is there? You have to do this curve. Okay. And I want to ask you at height H1 is equal to 2 meter, right? Over the same energy dh, how much water will be there? You have to integrate this one, right? So height at H2 2 meter, the water is more compared to 1 meter. Clear?
Clear. Clear.
Clear. And how to find out the height at H1 2 meter? It should be equal to n at 2 meter height into dh will give me the total water in this. Okay, see, I want to find out this water. It will be n into 1 meter height. n 1 meter height में कितना है? Okay, so what is the value of n at 1 meter height? Okay, into the same dh will give me the total water at height h2 in this dh. Now clear?
Clear. Clear, sir.
Anyone who couldn't understand now? Hello? Similarly, here I want to find out at energy E1, how many states are available in between DE? So I have to do NE1 into DE. E1 is how much? A1 into root of E1 minus EC. This is a curve. So here NE is equal to 2 meter. Means suppose if I approximate N is equal to this parabolic curve, it will be equal to A1 into 2 meter minus, suppose EC is equal to suppose suppose I don't know 1 meter. Okay, suppose 1 meter. Okay, so this will give me a value into dh will give me the water. right? And here if I want to find out 1 meter, suppose this is EC is equal to suppose 0.5 meter. Okay, guys, clear? Guys, clear or not clear? Hello? Hello? Hello, am I audible?
Yeah, you are audible, sir.
So the last one on the list, I'm telling, if I want to find out the same curve I'm approximating here, the total amount of water it has 2 meters, what I have to do? N 2 meters. Suppose EC is equal to 0.5 meter. Okay. So what you have to put? A1 into root over of 2 meter minus EC is 0.5 meter. Okay. Into DH. Okay. Similarly, from here, if I want to find out this water, it will be A1 into root over of N net to 1 meter is 1 meter minus 0.5 meter into dh. Clear now?
Sir, this is clear. I was actually asking this this formula A1 root E1 minus EC. How that from where we got that formula actually?
So see, but this is called modeling, right? So people have understood the physics, then they have approximated the curve in this. So you have to approximate this curve, right? This curve in a mathematical form.
Okay.
So this is the mathematical curve of this curve. Any.
Okay.
The simple mathematics. See, this is just a equation of a parabola.
Okay.
Guys, all of you got?
Got it.
So you understood? In summary, okay, you understood? These are the EC, this EB. So the allowed states are like this. This is my allowed state. Okay. So this is my NE. Okay. This is energy E. Okay. So this is approximated by A1 into root over of E minus EC. This A2 into root over of EB minus E. Clear? Clear. Okay. So you have some 5-minute time, or I will take next class. This is the last point, because out of 3 points, okay, you covered the first point, second point, and third point is remaining. So this is covered. What is allowed? How is the distribution? This is the last point. This is means you want me to cover? I can cover within 5 minutes. If you are all are means not tired. Yes.
I am not tired, sir. No problem. Please.
Chetra and Sheikh, Chetan, please tell me.
Yeah.
It's like
You can continue, sir. No issue.
so all are agree, na? I can continue, na?
For me, no problem, sir. Can continue.
Okay, so I will take just 5 minutes. So we will complete this all the 3 tenets. Then you can next class you can easily start things. Okay.
Yes, sir.
Okay, and also thing is since this is the initial class, right? So I have to tell you everything detailedly. Because later I can move fast. Okay. Otherwise later suppose you want to like understand a little bit more, right? We can take some extra classes also. But I want that everything should be very clear from your mind. It's not like I just give you the formula. I would have given you the formula directly. N is equal to NC into NC into exponential of minus EC minus EB by KT. So if you go to any other institutes, entire India, they'll directly give this formula. Okay, so you just mug up and go and vomit. But here, if you do not understand each and every particular term, right? So you will not appreciate and you are not able to use in the exam. Okay, and studying so much of thing and not able to utilize in the exam, I don't like this thing. At least you study how much amount of study, everything, whatever question will come, you should answer the question. So my aim is don't study 100%. If you study 70%, but if the question comes from the 70%, you have to answer the question. I don't know.
Right, sir.
Yeah.
Yes,
So
sir.
that is my experiences. Like for example, let me tell you one story. So I have completed my masters in IIT Kanpur with a gold medal from scoring 10 by 10. Okay. So also I have cleared the engineering service in 2019. Okay. And also I have appeared at least you can say 15 20 interest. Okay. So I have some experiences I can share you in the next class, but today time is not there. So in the next class you remind me how things are very important. Okay. So in exam, just studying something and going is not all. Getting me? So what are things important that I will let you know in the next class, but you just recall me. Okay.
Okay.
Okay. So let me just complete this thing. Okay. So also think that next class na I'll just give you a capsule of whatever you understood till now. Okay. So you might be thinking that you are understanding so many things. So if I just next time just brief you whatever thing you taught in just 5 minutes na, you will appreciate what are the four events. Okay. So you might not be connecting the pros. Okay. So I will next class in the beginning I will just tell you what is the thing we have covered till now, so that you can connect each and everything. Okay.
Okay, sir.
Okay.
Okay,
So
sir.
why I spend so much of time in this? Because this you can understand after few classes. Okay. So now you come to that thing that I have told that in the 10th floor, right? So I will take 5 minutes. Okay. In the 10th floor, we have understood in which floor how many number of rooms are available. Clear or not?
Clear, clear.
So till now you see. So this is my 10th floor. Like at which floor, at what energy, how many states are available? You understood or not now? Now till now you got out of 4 states, at what energy, how many states are available? Clear?
Clear, clear.
Clear. And out of the available state, they are available. So out of the available room, in which room people are there? You have to count. Suppose there are 100 rooms in the 10th floor. Out of 100 room, how many rooms people are staying? That will give you the number of people, right? Right or not? Hello? Hello?
Yes, sir.
Yeah. So thing is, I have to find out at what out of the available state, what fraction of the state are occupied. Suppose in conduction band, okay, I have foreign state. Out of foreign state, if I know how many states are occupied, I can get the number of electrons in the conduction band. Clear? Again, I am repeating. So in the conduction band, out of 4n states available, over the energy from EC to E top, out of the available energy states, how many states are occupied? Then I can get the number of electrons in the conduction band, na?
Yes,
Yes.
yes.
Yes,
Sure.
sir.
So this is nothing but Fermi Dirac function. Fermi Dirac function. Okay. Actually, I have to change my earphone next time. Okay. Okay. This is a Fermi Dirac function. What it tell? At any energy E, out of the available energies, how many energy states are occupied? Okay. So I'll just discuss about the function very briefly tomorrow. Okay. But just to let you, just before going, just tell you what is the importance of this function. Okay. In this here, you understand that here, okay, suppose this is energy U1. Okay, this is energy U1. Okay, guys. Hello.
Yes, sir. Yes.
And in U1, in D in between D, how many states are available? Quickly tell me. At E1, in between D energy, how many states are available?
2 states, sir.
Brother, telling D the energy range. DE.
D into
Guys, this should be very attentive. D into NE1, na?
yes.
So any the number of states at E1 into D will give me the total number of states available in a range D at E1.
Yes, yes.
Similarly here, total water available at height 2 meter is equal to So n at 2 meter into dh is the height. Similarly, here total number of states available at E1 in DE is the energy range into distribution function n at E1. Clear, guys? This is the
Clear.
number of states available at E1 in between DE. Clear? So out of the available state, how many are occupied? We multiplied by the probability that state is occupied. So this is the probability. This is F into ET. F into E1 into T. This will give me, this is the states available. So out of the available state, how many states are occupied? You have to multiply by the probability function. FET will give me the number of electron in range D at E1 in conduction band. Clear?
Yes.
Yes. So if I want to find out the number of electron in between D at E1, so this is the NE1 into D, the number of states. This is the number of states available. This is the number of rooms available into probability that out of the number of rooms available, how many rooms are occupied. This is the probability function. Out of the number of states available at E1, FE1 into T, FE1 is nothing but 1 by 1 plus exponential of E means you have to put E1 minus EF by KT is the probability. Okay, this you have to put this function to get the probability that out of available state, how many states are occupied. Okay, that will give me the number of electron in range D at E1. Clear? Hello?
Yes, sir. Yes, sir.
Yeah. So just last but not the least, before leaving, if I want to find out the total number of electron, I have to what you do? Integration of EC to E top. If I do this, then I'll get the total number of electrons in the conduction band. Correct? So this is the total number of states. At each point, how many states are occupied? Will give me the total number of electron in D. If I integrate, I will get the total number of electron in the conduction band. Right or not?
Yes.
So in the next class, we will discuss little briefly about what is FET. Okay, how this function is helping you. What is the function? Okay, what is Fermi level? Okay, what is the significance of Fermi level? Okay, so if you increase temperature, what will happen to Fermi level? Okay, and using this, we will get a very accurate estimate of concentration of electron in intrinsic semiconductor at any temperature. Clear? Clear. So using this in the next class, first we will discuss little bit more about this. Then using this integration formula, I will not integrate, just given you the theory, just you have to integrate, I will give you the direct formula. Okay, so I will not spend time spent in solving the mathematics. Okay, because I have to tell only the concept. The mathematics you can do later. Just I will tell you direct formula. Okay.
Okay, sir.
Okay. So tomorrow you come. I will brief everything till now, whatever you in 15 minutes, so that you will have a sequence of event in your mind. Okay. Now it is discrete in your mind. So let me tell you in sequentially, so that it will be very methodical in your mind. Then we will take the next class. Okay.
Yes, sir.
And just one request: tomorrow you come on time, so all stage is set, so that you can cover all the things that is planned.
Sure.
Okay. And actually we are one class behind the schedule. Okay, because today I was supposed to complete the extrinsic semiconductor. Okay, and if you understand the intrinsic, then extrinsic is very easy. Okay, and after extrinsic, then we have to understand if you get the concentration, then how the electron and hole flow in the semiconductor. That is called carrier transport. Okay, so after you get the concentration, then how they are moving. If you know how they are moving, then we are done. Then we will go to the diode. Okay.
Okay, sir.
Okay, so next class, hopefully we will try to complete the extrinsic semiconductor. Okay, for that you have to go and come with whatever things I have taught you. You come with prepare with everything. Okay, then if you have any doubt, you ask me, so that you can go very fast. Okay.
Sure.
Okay, so next class you study up to this much and let me know if you have any doubt. Okay. And just one last thing, like whatever I'm speaking now is okay to you or not? Means till now properly coming. I'm talking about the speed, not about my voice. I'm talking about my speed.
It's okay, sir. These are beautiful concepts cleared by you only.
No, actually, my thing is ki, actually I'm speaking a little fast, right? Like as you pointed. So I want to confirm ki whatever I'm speaking now it is very clear to you, or I'm again speaking very fast.
Yeah, that's okay. You are speaking in medium range only, but thing is that sometimes words comes no sir. You are due to the mic problem.
Okay.
Some words are missing.
So
And,
yeah, actually, in the last class, last time I have taken the class analog circuit. Okay, initial 1-2 classes, people were complaining ki I speak very fast. Okay, later on when I become little sooner, they got bored. Sir, you speak little fast. They are telling me. Okay, so it's like if I speak little fast, na, it will help you in the exam also to think more, think in a very fast. Okay, you should you should think little fast in the exam. Okay, that will very helpful for you to getting the marks.
speed is okay, sir. But thing is that mic problem, we are unable to get some words.
Okay, so
Yes,
I will
sir.
try to solve the mic problem. Okay, by having a another what we call different microphone. Okay, because I have to hold this, right. So I will bring another thing so that I need not hold this so that it will clear to you.
Okay.
Okay, so next class we will do this. Okay,
Tomorrow
we'll
also
go.
same time.
Pardon me.
Tomorrow also same time.
Tomorrow also same time. Okay, also what I am telling now. Suppose you don't worry about the syllabus. Okay, suppose we complete up to like see in the EDC, right. The fundamentals of this physics is only important. Okay, other things are easy, right? Diode and other things are you can easily like cover in quickly. Okay, because if you stage is set, na, you can really ramp up very quickly. Okay, and
Okay, sir.
if needed, I can take also 1-2 class extra also, not issue. Okay, at whichever time you tell convenient for you, I can take. Okay.
Okay, sir.
Yeah. Okay. Okay, guys. Good night. So thank you for patiently listening. So we'll try to improve the mic and my speed next class. Okay.
Okay, sir. Good night.
Okay. Good night,
Good
all of
night,
you.
sir.
Good night.
Good night,
Good
sir.
night. Good night.
Thank you.
Good night.